Once again, it's the Physics 105A video lecture. Physics 105A video lecture 14. And we're talking about scattering, and we'll continue on with that. Got some really interesting stuff today. So, I'll just unfold the whole scattering problem again. We're going to set up the Rutherford problem, Rutherford scattering, but we'll go back to what we had last time. So, scattering. We have a target here. There's our center of potential, and I'll do a dotted line. And coming in from infinity, there's a particle here, mv0, coming in from infinity. And it is a distance b above this axis. And if there were no force here, nothing to produce a force, it would just blow by here. However, it's going to veer off because there's a repulsive force typically. And I draw this trajectory, it looks something like that. So it came from infinity, it's going to go back out to infinity. And there will be a point of closest approach here that we can call r min because we're using plane polar coordinates. Okay, so you call that r min, and there's an angle here, phi0. And this thing goes on out to infinity, so that's asymptotic there. There's an angle theta, and because of the symmetry that the central force problem gave us, this angle phi0 is repeated right there. So that's what this particle does, comes out from infinity, goes out to infinity. In terms of central force problems, this was one with positive energy, right? Because out at infinity, the potential energy goes to 0, so it just has the kinetic energy out at infinity, same when it goes back out to infinity. Over here. Okay, so that's the scattering problem. And just based on these definitions, we see that 2 b naught plus theta is equal to pi. We make use of that. And the problem was of analyzing the particles scattered here. So we can imagine we're going to have detectors set up to discover these particles, and the detection will be at a certain angle. We'll be able to count certain numbers of particles. We can imagine sweeping the whole detector around. The thing's symmetric, so we could go from theta equals 0 all the way to theta equals pi, which would be a particle that comes in and goes straight back out again in the same direction. Good. So we have an area, an annulus. Okay, we've got an annulus here. And a certain number of particles pass through this ring. And those self-same particles that pass through the ring here are going to pass through some corresponding ring, we could say, annulus on this side. So on this side we have a cross-sectional area 2 pi b db. But we're interested in what happens over on the theta side here. So we transform this 2 pi b of theta db d theta d theta, and we're interested in the positive value of this. So you take the absolute value. So this is the differential scattering cross-section. And the example I had given for the homework and that I had worked through was for a hard sphere, but when we do the Rutherford problem, we know it's not a finite hard sphere, it's a very infinitesimal nucleus. Good, so what else do we have here? There's the expression we're going to try to find. We had energy was equal to 1/2 mv0 squared, because we're coming in from infinity, and we had angular momentum was equal to mv0 times b. Okay. So the first thing we do, calculate v sub 0, then we have v sub 0 is equal to pi minus theta over 2. And then for the third thing is we then calculate d sigma, this expression star here. Okay, so like I said, the one I did for you guys was with a hard sphere, and I didn't actually have to do the central force calculation of this here, but I'll write down the result because I had set it up last time, and so I'm doing it for you if you haven't gotten to it yet. But it's the integral r min. So I had set that up and I had pointed out these substitutions. So you plug those substitutions in, r min to infinity, right? That's 1/2 of these trajectories, r min to infinity. And then we would have b dr over r squared divided by root 1 minus b squared over r squared minus u. This one here is just the kinetic divided by, potential divided by the kinetic, so 2mv0 squared u of r. Okay, so that was the expression we were going to obtain. Yeah. So we're going to go ahead and put a box around that and talk about that for a moment, because we've done this a few times now, and this is a nice form. So for the hard sphere problem that I assigned the other day, here's what I was talking about. U of r is essentially identically equal to 0 for the hard sphere problem. So you pull that out, you can kill that, and it's identically equal to 0 because we're integrating from the radius a out to infinity. And so then you can see you're just a transformation away from your inverse sine. On that problem, we're doing the inverse sine. And, you know, I'll even put the plus minus here. And good. So that was for the hard sphere potential. You just kill this. Now for the Rutherford problem, we're not going to throw that away at all, right? We have to deal with it. So that's what I'm going to go ahead and put up here next. Tempted to keep this expression up here. Tempted to keep it all up there. Let's see. For the Rutherford problem, I will just put up some intermediate results. They won't even fit in here. Yeah, okay. So now Rutherford scattering, I'll just write Rutherford. So everything's already been built in here. So what we have to do is plug in u of r, and u of r is equal to alpha over r. So if alpha is positive, there is your repulsive potential, repulsive force, alpha over r. So you go in here, and this is essentially the calculation we did for the Kepler problem. Okay, it's going to be rearranged. You're going to do your substitution. This lowercase u equals 1 over r. Turn this thing into an inverse cosine again. And what we find is phi0 is equal to inverse cosine of I'll write this down to make sure I get it right. Inverse cosine alpha over mv naught squared b, alpha m v naught squared b, root 1 plus this thing squared. Let's go ahead and make a little more room. 1 plus, there we go, 1 plus alpha over m v naught squared b, the quantity squared. There we go. Okay, so that's the result of our integration. Of course, now we've got our work cut out for us because we have to do this. So I have an intermediate result for us on that as well. And that would be that inverse cosine. And then, of course, we're going to use this. Okay. So now your phi naught, of course, is going to be exchanged, written in terms of theta. So now what's our other intermediate result? We're going to get b squared is equal to alpha squared over m squared v naught to the 4th, and then we've got a tangent squared of phi naught. And I want to put up the entire Rutherford formula. I guess I got to make some room here after all. Okay, so I want to put the result up and discuss it a bit. But yeah, let's keep a little bit of this up here. We have d sigma 2 pi b theta magnitude dB d theta d theta. Okay, so what is our result? And we can discuss this a bit. So we're going to end up with d sigma equals pi alpha over m v naught squared more room here, cosine theta over 2 sine cubed theta over 2 d theta. Okay, put the box around here and see what it is we're looking at. So this expression is pretty non-trivial. It's going to take a little bit of monkeying around to get this, but all the steps are there. All the steps are clear. You got some trig substitutions. Now, this thing cannot be integrated. Okay, if you were to try to integrate this thing from 0 to pi, you see immediately the sine theta over 2, let alone sine cubed, is going to give you a diverging integral. Yeah, so what does that mean physically if this thing diverges? You can still sweep your detector around and compare relative amounts detected at one angle versus another. Okay, that is still open to you. So regardless of being able to integrate this thing completely, you have this function, and at different places, the number detected will be proportional to this expression d theta for some finite d theta. So yeah, this is a diverging quantity. That means it's a long-range force. The reason when we had this hard sphere, we got the literal cross-sectional area as the differential, as the total cross-section, is because that's an ultra short-range force. Hard sphere potential is the shortest possible range force. But here you have Coulomb's law, which goes out to infinity. Good, so, but anyway, that's a great result to be had. So this is a real classic calculation. And I think everything here is really transparent if you look at both of these lectures now and just work your way through these steps, how we constructed this object, this thing right here, This is just our integral we've done many times. We've looked at this many times, but we specialized it for this particular scattering problem, so it really takes on a good look right there as well. Okay, so I'm just leaving that as the major remaining problem of this semester. So from here on out, we'll do a number of things, but also we'll try to tackle some review at this point. So I have one more lecture this week and 2 more next week. We'll do review on those. And I will get into many particle systems actually, because the material there and the skills for the many particle systems really reinforces what we've done so far this semester. After I erase this, I do have a nice, not application of the scattering formalism, but a slightly different cross-sectional type of application. Namely, I want to do something about an asteroid collision. Suppose an asteroid is headed towards the Earth or towards our vicinity. What are the criteria for it colliding with us or not? So that's my next topic here, just to make a dramatic asteroid collision. And see if I can remember how that goes. Okay. Okay, I didn't write homework on the board, but that was the homework problem. Just find out everything I put here as those results. Now, let's just call this asteroid collision. So what we're thinking of is a small object colliding with a finite spherical object, and that finite spherical object could be our Earth, and the small object could be an asteroid. And the thing about it is, it's just not a matter of being aimed so that they're going to be at the same place at the same time. Okay, so it's not just that their orbits intersect exactly, but Newton's law of gravity is attracting the asteroid, so it doesn't have to be heading straight on. It has to come close enough, and then it'll be drawn in. So that's what we're going to look at, and we'll set it up just like this collision, similar to the collision we just did, with an attractive potential. So here is our finite body. I think I need about half the board for this. Okay, so here's our finite body of radius capital R, mass m for whatever it's worth, mass m, radius capital R. And we have something, here's our asteroid, and we'll use this impact parameter b again. So it's coming in this direction, and it's got the mv naught that the other one had. But is it just going to blow by? If it's going fast enough, it would. But the worst possible case scenario is that it just hits head on somewhere, and the boundary between those two is if its orbit, how about another color for the orbit? If its orbit is such that, let's draw a sweeping curve, it just grazes. Okay. So then you could say R is equal to capital R if it just hits. So that's the difference between colliding and not colliding, right? Had it had a slightly farther orbit, it would have not collided. So there's our criterion right there. So we've got mv naught, and therefore E is equal to 1/2 mv naught squared. L again is equal to mv naught b. And we want to find the cross section. You could say pi b squared for which this collision occurs. Good. So once again, we're back to our central force. So what we're going to do here is remind ourselves we've got 1/2 m r dot squared. Let's make that a proper r. 1/2 m r dot squared plus L squared over 2m r squared plus u of r is equal to E. Now, at the point of collision, in this limiting case here, that is the closest point where r is equal to r min. R is equal to r min, and r dot is equal to 0. So in the analysis of this expression, r dot is equal to 0. And L we have an expression for, and U of R we know is the Newton potential. And I'm not quite sure which way to do that. Well, we'll just call it alpha over R minus alpha over R for the moment. We could plug in Newton's law after that. Good, so the R dot 0, what about the L? We have m squared v naught squared b squared over 2m capital R squared. We have minus alpha over R, because again we're at that R equals capital R, equals 1/2 m b naught squared, because we were approaching from infinity. Same as before. I could put some words up to that effect in a minute. Yeah. So the cross section we're looking for I'll call it sigma total equals pi b squared. That would be the total cross section for which a collision occurs. So really we just have to solve this expression here for b squared and see what happens. Okay. So let's do that. First of all, we've got rid of an m right there. So sigma total equals pi b squared equals pi, and then that b squared is equal to r squared b squared, I'm going to have 2r squared over b naught squared times 1/2 m b naught squared plus alpha over r. So yeah, if we can just simplify that thing enough, we'll see what we've got. Okay, I'm going to use this piece of board. So what do we have here? Sigma total equals, we have, didn't I have an m here? I had an m, 2r squared over m b naught squared. So yeah, get a nice cancellation here. Okay, m v naught squared, 2. So I'm just going to have pi r squared, and then we'll add something to that. Plus pi, yeah, I'll just write this out, 2r squared over m v naught squared alpha over r. Yeah, okay, let's go ahead and get rid of this and write this out one more time. cross-section of this is the following. We've got pi r squared, and if I factored out a pi r squared, we won't factor it out. So we'll have 2 pi alpha over m v naught squared. Okay, provided we did this right. Okay, this is good enough to have a little discussion on. So, you'll notice that if v naught is really large, and these relative amounts, we could work around with this a bit, but I'm just the qualitative discussion here. If v naught is really large, then this second term is suppressed. That means this bullet just blows right by the target unless it happens to be aimed precisely at the target. Okay, so the cross section in that case would just be pi r squared, the physical cross section of the target. But if as v naught is smaller and smaller, this cross sectional area will exceed this actual pi r squared by any amount. And that makes sense as well, because if v naught were 0 and we're out there at some great distance, then eventually these two things are going to find themselves in the head-on collision. So yeah, it depends on the relative speed that's going on there, and of course the strength of the gravitational potential and the radius itself. Okay. If one were to factor out a pi r squared, then you could have pi r squared times 1 plus something, and that's also a good, that'll actually give you the criterion of what is great or small with respect to that 1. So that would be a good thing to do as well. But yeah, this is just the first pass at the asteroid collision problem and whether or not we're going to collide. Okay. Good, we're going to leave it at that. So the main thing is to get the hardcore potential problem. And then once you've done that and feel good about that, then try out the Rutherford problem. And it's a classic, you can look it up all over the place. But it's worth it. So I'd say this ends our central force treatment, and we've done quite a bit. Good, so we'll leave it at that. We've got a couple more lectures to go, so just keep taking those good notes, and see you next time.